Okay, so we are doing chapter number 20, and in that chapter, we have discussed permutations. We have defined them as a bijective function from a set to set, and then we have defined some properties of that permutation over here in proposition 20.2. They are same properties for which we check for a group. Group is an algebraic structure. And then we have defined the cycle notation for the permutations. So it's a like concrete way of writing permutations into the cycle notations. Then we have said that every permutation in the set Sn can be expressed as a product of disjoint cycles. Disjoint cycles are those cycles which does not have any common element in the cycle. Okay, then we have defined the order of a permutation. So the power which we give to a permutation in a cycle notation, and that power is something, if we give that power to a permutation, it will become an identity permutation. Then that power is going to be an order of a permutation. Now we are going to talk about that which permutations are even and which are odd. Okay, so let's start with an example. Okay, so let's take n is 3 and let the variables x1, x2, x3 be 3 variables. Now we will let the permutations in S3 move around these variables just as they move around the numbers 1, 2, 3. So for instance, so we can say that take permutations in S3 and apply on these variables. So the permutation 1, 2, 3 or 1, 3, 2 sends x1 to x3, x3 to x2, and x2 sends back to x1. Now define the expression. So let's take an expression delta, which is x1 minus x2, x1 minus x3, and x2 minus x3 again. Okay, now we can apply permutations in S3 to delta in obvious way. So apply permutations in S3 to delta as follows. So that is that 1, 2, 3 sends delta to, as you can see, we have x1 minus x2. So 1 goes to 2, and then 2 goes to 3. We will keep the signs same, and 1 goes to 2, and 2 goes, 3 goes to 1 again, and then 2 goes to 3 minus 3 goes to 1 again. And now notice that this is just the expression for delta with two brackets. Two brackets reversed. So you can see that we have x2 minus x3 similar. So these are same, but we have reversed the brackets, this one and this one and this one and this one, right? We have reversed them. So you can say that this reversed two brackets, x2 minus x1 and x3 minus x1, right? Now, so 1, 2, 3 sends delta to delta. So you can say, so the permutation 1, 2, 3 sends delta to delta because if you write x2 minus x1 is minus x1 minus x2 and x3 minus x1 is minus x1 minus x3, then delta is going to be from there, you will have minus x1 minus x2 and minus x1 minus x3 and x2 minus x3, which is nothing but if you just multiply all these signs, you will have delta again. So this permutation sends delta to delta. Perfect. However, if we apply the permutation, if we apply 1, 2, and 3 fixed to delta, we get x2 minus x1 and x2 minus x3 and x1 minus x3, which is, so see, the first delta was x1 minus x2. So now we have x2 minus x1. Second one bracket is x1 minus x3. Now we have x2 minus x3, which is there. But so I can say that this is there and this is also there. But now this one is changed. So you can say we have minus x1 minus x2 and everything else is similar. Just placed at different places. So this is minus delta. Perfect. So you can see that each permutation S3 sends delta to either plus delta or minus delta. So each permutation in S3 sends delta to either plus delta or minus delta. And here's the table. So we have G, and then we have delta of G. So we have a permutation identity, then we have permutation 1, 2, 3 fixed, 1, 3, 2 fixed, and then we have permutation 2, 3, 1 fixed, then we have 1, 2, 3, and 1, 3, 2. Now, if we apply identity, it will send delta to delta. If we apply 1, 2, and 3 fixed, then it just give us minus delta. Similarly, 1, 3, 2 gives us minus delta. But through 2, 3, 1 also give us minus delta. And this will give us delta and delta. So let's say this is a table. So S3 give us these signs. So we shall call those permutations that send delta to plus delta even permutations. So you can say those permutations that send delta to plus delta are even permutations. Even permutations. And those permutations that send delta to minus delta are odd permutations. Right? So I 1, 2, 3, 1, 3, 2 are even. And 1, 2, 3 fixed, 1, 3, 2 fixed, and 2, 3, 1 fixed are odd permutations. Perfect. Now the definition of even and odd permutation for general N is very similar to the example. So let's say let x1 up to xn be variables, and take permutations in the set Sn to move these variables around in just the same way. Same way they move around the symbols. One to n are defined to be the product of all. Define delta to be the product of all xi minus xj for I less than j. The notation for this is that delta is now the continued product between I less than or equal to j, sorry, 1 less than or equal to I is less than j, and j is less than or equal to n xi minus xj. Now the symbol, this means this, the continued product, the product of all the terms. Just as in example, we can apply any permutation G in Sn. So we can apply any permutation G in Sn to delta, and the result will be either plus delta or minus delta. Now define the signature of del G. Define the signature of G to be the number SGN of G, sign of G inside the set plus 1 minus 1, such that G of delta is sine of G into delta. Now this defines the signature function. Find the signature function, which is a function SGN from Sn to the set plus 1 minus 1. Okay, so let's give a definition. The definition is a permutation G in Sn is an even permutation if sine of G is positive and is an odd permutation if sine of G is negative. Perfect. That's how we define the even and odd permutation. So it is not immediately obvious how to calculate quickly the signature of an arbitrary permutation. Clearly, it would be a bit of a pain if we had to work out what G of delta would be. So fortunately, there is a somehow more clever method available if it is based on the following result. So in the statement of part 2, a 2-cycle AB just means that the permutation in Sn that swaps A and B and sends everything back to itself. So that we call a 2-cycle. So if you want to see the example, let me show you. So all those odd permutations in S3 are 2 cycles. Okay. Now let me give you the proposition. So the proposition says for any permutations G comma H in Sn, we have sine of GH is sine of G sine of H 2. So this is 1. This is 1. 2 is the signature of any two cycle AB is -1. Always. Okay. Now, it's easy to prove, but there is a lot to discuss in this chapter. So we will try to give another proposition, which will try, like reduce the amount of calculation to find out which permutations are have positive and negative signs. So the other result is proposition 20.6 is the signature of any R cycle in the set Sn is equal to -1 power R -1. Now this is very nice to this is a very nice result, because if you have an R cycle, then you can prove that every R cycle can be written as the product of two cycles, disjoint two cycles, and we have already done that. So what you need to do is you just need to multiply the R cycle as a product of disjoint two cycles, and then you need to find out if you need to find out the sign of an R cycle, you just need to multiply the disjoint two cycles and find out their sign. So we know that from proposition 2.20.5 that the signature of any two cycle is -1. So imagine you have a R cycle that can be written as a product of 5 disjoint two cycles. Then you just need to multiply -1 5 times. If you have a something like R cycle, which can be written as a product of 4 disjoint two cycles, then you just need to multiply -1 4 times, and then you will get 4 plus 1. And if you multiply it odd times, you will get -1. So that all depends on that how your R cycle can be expressed, right? So let me just give you a glimpse of this. That suppose we have R cycle that is A1, A2 up to AR. So you can write this R cycle as a product of disjoint cycles as follows. Okay, this is not 2 but R. And here you have 2. So all these are 2 cycles. Okay. These are 2 cycles. So you just need to multiply them, their sign, and you will have the sign for the R cycle. So you can even say that this is a R cycle, right? Okay. Now there is a result again. Proposition 20.7, which gives us the sign for an R cycle. So it says that if G in Sn has cycle shape R1, R2 to Rn, then sine of G is going to be -1 power R1, -1, -1 power R2, -1, product, -1 power RK, -1. If this is RK also. RK -1. So G is even permutation if and only if the number of Ri that are even that are even is an even number. And I'm gonna explain it more in the example. So let's talk about it. An example 20.9. So example 1 is the permutation which is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11 in S11 is odd. So if you see this, now remember, you can always break a 4 cycle. So this is a 4 cycle into the product of 3 2 cycles. Okay. And similarly, you can always break a 3 cycle into the product of 2 2 cycles. Right. And then we have 2 cycles. So see, so we can write this in 3, this in 2, that is 5. And then we have 8, 9, which is 6, and then 10, 11, which is 7. So if you multiply 7 and -1 7 times, you will get -1. So that means that the sign of this permutation is odd. Clear is that? Now we will give another example, which is the permutations in S5 by something called in a table. So let's draw that table. So we have cycle shape, and then we have number. So you say the permutations in S5 that are even are precisely those cycle shape, those that have cycle shape 1 power 5, 2 square 1, 3 1 square, and 5. And then the number of these is 1, and there are 15 cycle shapes of this type. and there are 20 cycle shapes of this type, and there are 24 cycle shapes of this type, and then this number adds up to 60. So that means if you work out in S5, okay, in S5, these are the even permutations with following cycle shape. Okay. Now there are 60 permutations which are even, and if you find out the order of this is 5 factorial, which is 120. Okay, and if 60 of them are even, which is equal to, then 60 are even in S5, which is one half the order of S5, which is one half the 120, that is 60. So for any n, exactly half of the n factorial permutations in Sn are odd and half are even. So you can say in any n, exactly half of the permutations, half of n factorial permutations in Sn are odd and half are even. Okay. So then this means that in group theory, let me give you the glimpse of group theory. In group theory, the half of n factorial permutations form a very important subgroup, very important subgroup. Now, those are the terms you will learn in group theory of the set Sn, which contains all of the permutations of n factorial, known as alternating okay, perfect. Now let's talk about a very particular example to talk about these things more. So, and there is another topic in which even and odd permutations play a very key role, is the theory of determinants of n cross n matrices. So now let me give you an example, an interesting one. We call it the 15 puzzle. You can learn about it more from internet. This puzzle consists of 15 square blocks, 15 square blocks labeled from 1 to 15, arranged in a 4x4 frame with one space like this. So, so we have a block which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So remember the game in which you wanted to make a shape by joining some shapes, some random shapes, and try to make a picture. And in that game, there is always one space empty. So this is a same kind of a game, okay, a puzzle. So to make a move, you slide one block into the space, thereby creating a new space. The problem is this: can you make a sequence of moves to change the above configuration to this one? So the problem is this: can you make a sequence of moves to change the above configuration to this one? Which one? This one. So you have 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Can we do that? Answer is no. No, you can't. Here is how to prove this. So denote this box is an empty box, so that the initial arrangement is this. The initial arrangement is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then an empty box. Now, moving a number x into the space corresponds to a doing a two cycle. So we will get, by moving, we get a two cycle, that is x comma this empty cycle. Now, if we do a sequence of moves and end up with an arrangement with delta in its original place, then delta must have been moved upwards the same number of times as the downwards, and leftwards the same number of times as the rightwards. So the total number of moves must be even. Since each move is a two cycle, this means the effect of the sequence of moves is a permutation, that is a product of an even number of two cycles. So by proposition 20.5, this must be therefore an even permutation. However, we are looking at a sequence of moves that affects the permutation. So which permutation we are talking about? We are talking about a permutation which is 1 to 15, 2 to 14, 3 to 13, 4 to 12, 5 to 11, 6 to 10, and 7 to 9, 8 to 8, 9 to 7, 10 to 6, and 11 to 5, 12 to 4, 13 to 3, 14 to 2, and 15 to 1. This permutation we are talking about, right? Now, in the cycle notation, this is in cycle notation. This is 11, sorry, 1 to 15, and 2 to 14, 3 to 13, 4 to 12, and 5 to 11, and 6 to 10, and 7 to 9, and 8 is fixed. But this is a product of 7 2 cycles. So this is product. This is a product of 7 2 cycles, and hence an odd permutation, and hence is an odd permutation. Therefore, there is no sequence of moves that can affect this permutation. So in conclusion, you cannot convert the this one into this one. Okay, perfect. Thank you so much. Bye.